Hello, everyone. Greetings. This is Volts for June 10th, 2026. Why is NERC so worried about data centers? I am your host, David Roberts. Traditionally, the grid planners and regulators charged with maintaining the reliability of the wholesale power grid concerned themselves with the behavior of generators, ensuring that power plants do not ramp up too quickly, trip off too suddenly, or create unmanageable frequency or voltage disturbances. Loads, even large industrial loads, were presumed to be relatively safe, as they tended to behave quite predictably. That has changed with the introduction of gargantuan data centers, which can ramp extremely quickly, trip offline very suddenly, or induce oscillations that mess with grid voltage. They are big enough and unpredictable enough to cause problems that can cascade and cause widespread blackouts. Grid regulators are taking notice. Last month, the North American Electric Reliability Corporation, or NERC, the nonprofit regulatory authority assigned with maintaining the reliability of the U.S. wholesale electricity grid, issued a Level 3 warning about data centers, which, in the typically boring regulatory world, amounted to a flashing, blaring siren. It called out the increasing threats that data centers pose to the grid and issued, alongside the warning, a set of recommendations for grid planners, transmission organizations, and hyperscalers to address those dangers. This amounts to a historic structural shift in how grid reliability is conceived. For the first time, there are loads big and powerful and weird enough that they simply must be drawn into the world of grid planning and reliability. It's going to require updating all kinds of regulations and assumptions, and hyperscalers aren't necessarily going to be happy about it. To discuss the warning, the recommendations, and the many associated implications, I have with me today Colin McCormick and Doug Bryan, respectively the Chief Science Innovation Officer and the Senior Energy Modeling Expert at Carbon Direct, a firm that provides advice and counsel to utilities, tech giants, and investors pursuing clean energy. We are going to talk about what triggered NERC's fears, what they want the industry to do, and how this might change the pace of data center build-out. With no further ado, Colin McCormick and Doug Bryan, welcome to Volts. Thank you so much for coming.
Thank you, David. Pleasure to be here.
Great to be here, David. Thanks.
There's so much to chew on here, guys. So maybe, Colin, I'll start with you. There have been big loads on the grid before. There are lots of big industrial loads out there. Think of like steel plants, things like that draw a lot of power. But there's something new and different about what NERC calls computational loads, which is, I think, mostly data centers, but it's also the crypto guys. Big computational loads. So let's just start with what is it that these big computational loads are doing that is different and that has NERC worried?
Well, you are right that we have had big loads on the grid before, industrial loads, although it is worth noting that even the largest industrial facilities historically have not drawn power at the scale that some of the frontier data centers are doing. So there is a scale issue. But the more important issue is the nature of that load. And you referred to it as, I think, big and weird. And it's that weird piece that is important to get your head around. So the way a data center looks to the grid is a lot different than the way an industrial load that has a lot of rotating machinery, motors, et cetera, looks to the grid. The data center interfaces with the grid using power electronics, using active electronic equipment, uninterruptible power supplies, essentially, that are doing a couple things. So they're active, they are sensing in real time the voltage and the frequency of the power that's coming from the grid. And their job is to protect the expensive, sensitive computing equipment that they are passing that power through to. And they are designed to be very proactive in protecting that expensive equipment. They're designed to react to very minor fluctuations, what a lot of grid planners would think of as very minor fluctuations to voltage and frequency. And if they detect those, they follow a particular standard. We can get into the nerdy exact standards later if you'd like, but they follow a particular standard that essentially has them trip offline, disconnect from the grid, and serve their computational load using backup power or storage. And that tripping offline happens in an incredibly fast, incredibly brief period of time, 20 milliseconds or something like that. That's extremely different from the way a conventional industrial load would respond to any fluctuations.
Right. And as you were saying, some of these loads are like they're gigantic. It's like
Well, yeah,
like 100 megawatts or whatever. So that's 100
and up.
that's 100 megawatts of load just vanishing basically in the blink of an eye.
That's right, and that's a big number. Now, Doug can get into this in a minute, but the grid is designed to handle a certain amount of load tripping off, and 100 megawatts, big as it sounds, is actually not outside the realm of what many grids can respond to. But we're talking not only about single data centers tripping off, we're also talking about the possibility of multiple data centers tripping offline to the same event.
Right, because if they're all on the same grid, they're all sensing the same fluctuations and they're all
Exactly.
responding the same way.
Exactly. And maybe, Doug, you can get in a bit to how the grid is sort of supposed to handle this, but then we can think about how the scale is really very different.
Yeah, so the grid operators, they have tools at their disposal to handle these sorts of fluctuations. Like we don't have a static load profile throughout the day, let alone over the course of a year. So these sorts of fluctuations is something that the grid operators are designed to handle. So
Right, and generators have been known to fail and trip offline, which is sort of like
Exactly.
the inverse problem, but similar.
And there's what we call ancillary service markets that are essentially designed to respond to those large events. Why this is different is the scale of the drop. So you mentioned 100 megawatts, David. We're talking.
That was way too low. That was a way too low number.
Yeah,
It did not sufficiently impress the audience, I think. Let's call it a gigawatt.
At least.
And that's what NERC are responding to with the level 3 alert is gigawatt plus scale drops off the grid. And it is that scale that is a challenge. And you're also right that because it's a load drop rather than a generator drop, there's some nuance to how these ancillary service markets are designed to respond. And they aren't as well set up to deal with the load dropping as much as the generators, as you mentioned.
So that's the sudden disconnect of one or even multiple data centers, I think is the main thing here. But there's some other things too, some of which I don't fully understand. Let's talk about some of these terms. This is the one you're referring to as correlated simultaneous disconnection, which is a bunch of data centers going offline all at once. But there's also concerns about ride through and clustering, training bursts, low inertia. Maybe we could just mention some of these other weird features.
Yeah, I mean, I would categorize them, like if we were to use an umbrella term, it is still all related to the kind of ramp up and down of load on the grid system.
They all are basically about that.
Yeah, so like for example, the training bursts, that's a function of, AI training loads and the various stages that they hit through the training process. Sometimes they ramp up the GPU use as a function of the part of the problem that they're looking to solve. Sometimes they ramp down at a similar extent. So that's part of it, is like the scale of the ramp rate, as we call it. So the scale of the load change. And then what we were talking about at the beginning is these tripping off the grid altogether. So the load is maintained, but it's actually moved behind the meter. It's moved to these uninterruptible power supplies, shift that load in order to protect the very expensive GPUs and other IT equipment. And the argument there is that they're tripping off too easily, and that NERC is saying there needs to be a standard for, or there needs to be processes in place that allow for that ride through, as you mentioned. So maintaining connection to the grid even during these sorts of events up until a point. There will be a point at which they allow for it, but they think it's happening too easily at the moment.
Right. And I think we've already said this, but I'll just emphasize it one more time, which is that you can have multiple data centers. They're all sort of being coordinated by the cloud, kind of. So they're all like, if like one's ramping up, they could all be ramping up really quickly and they could all be disconnecting really suddenly. So it's not even just like one big data center is the threat. It's these clusters of data centers. I mean, you get a cluster of gigawatt data centers, then you're like 2 gigawatts, 3 gigawatts, all of a sudden you're just like beyond anything ever contemplated.
With similar sensitivities to dropping off and located in a similar part of the grid, that spells trouble.
David, it's worth noting that this isn't even necessarily data centers being coordinated in the cloud. They're sensing the same electrical grid conditions, so they don't need to be coordinated in the cloud. They're responding to the physics of electricity flow on the same physical grid. And the synchronization has to do with the fact that they're all programmed to respond the same way to those grid conditions.
And so this is not, we should say, theoretical. This is not
No.
a theoretical concern about things that might happen. So just talk a little bit about what has happened that has caused NERC to sort of slightly panic like this. Like these dangers have come to pass various places.
Yeah.
Tell us, like, what are some of the examples that NERC is responding to?
Yeah, you don't get a level 3 alert from NERC from a theoretical problem, I think is the way to put it. Yeah, so the direct response is, so the incident that's often referenced is in Virginia, of course, Data Center Alley, ground zero, really. So in the summer of 2024, a kind of minor equipment failure on a transmission line led to a very brief series of voltage dips on the transmission grid. These were so minor that it wasn't particularly noticeable, like the lights didn't flicker or anything. You or I wouldn't have noticed it. But the data center UPS, the uninterruptible power supply systems, noticed and took that automated action that we've been talking about. And they did it at a gigawatt scale. So we're talking 60 data centers. I think it was around 1.5 gigawatts effectively simultaneously dropped off the grid in response to that single transmission fault and switched to on-site generators. So that mass reaction was kind of triggered by these mechanisms that we've referred to, and it forced PJM, the grid operator, as well as Dominion, to scale back the output from power plants in order to protect the grid infrastructure, which was essentially to avoid a worst case scenario of what could have been cascading power outages in the region.
Yeah, and we've talked before on the pod about inertia, about these large spinning masses that are sort of there to absorb, these brief fluctuations. But you are just not going to have enough spinning masses to absorb 1.5 gigawatts. Even trying to ramp back power plants, like how quickly can PJM ramp back 1.5 gigs of power plant output? Like literally, how long does that take?
Well, that is definitely not happening on a second's time scale.
Right.
Is the point here. And, it's worth noting that the generators, for a long time, as you mentioned earlier, the generators had to develop the ability to ride through some of these disturbances and continue to generate power. And they're subject to a very specific different standard that requires them to be robust against some voltage and frequency fluctuations. So part of the way to think about this is the kind of the mismatch in tolerances right now between the generator side and these large data centers. The large data centers basically trip off at the first sign of trouble. The generators ride through, and I've got a pretty severe instantaneous imbalance between generation and load. So I really need to align those ride-through conditions better between the generation side and the large load side.
right? Which means regulators, the people in charge of reliability, have to start dealing with these large loads, which they've more or less not really had to like pull into this whole world before. That's the kind of the shift we're talking about.
Yeah.
And I do want to clarify one thing. Like, would you characterize this as the people in charge of computational load, like doing something wrong, behaving irresponsibly, or is this just sort of like something that's happened, sort of like inherent to the technology? Like, in other words, is there blame to be apportioned here?
I mean, I think, the deployment of the data centers and how they're responding is going to be a function of the processes and procedures that they are exposed to as regulated entities. What was interesting in basically what triggered the level 3 alert on the regulation side. So obviously we've got the challenge on the grid. On the regulation side, NERC, as part of like the previous alert, there was a level 2 industry recommendation. They did a survey to basically look at, of the grid operators, transmission owners, distribution providers, do they have sufficient processes, procedures, or methods to address the risks associated with computational loads? And the results were fairly robust that on the whole, the answer is no. I think it was 87% of transmission owners and distribution providers don't have clear facility design, modeling, and performance criteria for large loads in their interconnection requirements. So it's largely, the change in the grid is so rapid and at such a scale that the regulation is trying to meet the moment, I think is how I would phrase it.
A familiar story here on Volts, which is these really massive, huge, rapid changes in an industry and a sort of regulatory world that was accustomed to moving at a rather sleepy pace. And like, that's yet another mismatch. Like, everybody in this world is having to just move a lot faster than they are accustomed to moving.
And listen, I don't want to say that the regulators are sleeping at the wheel. Like, what is done in the grid operator room is frankly, it's wizardry.
Yeah.
To ensure that the grids continue to be reliable. But it's a real step change in what they're being asked to deal with.
Well, this is a little bit of a side question, but you kind of teed me up a little bit there, which is I've been wondering. So, like, the whole problem here is that these things are happening faster than operators can respond to. And I sort of have been wondering, like, is there any prospect that if operation of the grid becomes more software-based and digital and sort of faster, if there's any prospect of them catching up and being able to move faster, or is this all going to, for the foreseeable future, is it all going to be about trying to slow down the changes on the load side? Do you know what I mean? Like, is there a prospect on the horizon of sort of like faster, more digitized operator responses?
I think there are groups looking to answer that exact question or this exact problem with technology solutions. And it's largely through what we would probably traditionally call load flexibility or demand side response, and is about ensuring that there is greater communication between the data center operator or whatever the computational load is with the grid operator and the utilities. I mean, that was one of the direct recommendations or the essential actions from NERC, was having basically, I think they even said it could be done via phone if you want, like having a direct line of communication between the grid operator and the data center operator.
But like, nobody's going to make a phone call in seconds. Do you know what I mean? Like, you're not going to have a human being who's ever going to be able to react within milliseconds. Only software could possibly do that.
David, I think this points a little bit to the push for more ride-through capabilities. Trying to say, hey, data center loads, maybe you do need to be more tolerant. Maybe you need to slow down that sort of instantaneous trip off to be a little bit more compatible with response time that's feasible on the grid. So that's the spirit of that sort of direction of solution.
And I want to talk a little bit later about how the data center people feel about that. But one other question, which I was not, reading through all these PDFs, was not totally able to wrap my head around, is how do inverter-based generators play into all this. So last year, NERC issued another issue 3 alert. Poor NERC is like has become quite neurotic. Last year, NERC issued a level 3 alert about inverter-based generators, which, for listeners' benefit, is just basically like solar and batteries and some wind, I think, effectively renewable energy. I know they issued a warning about them, and I know somehow like all this stuff about computational load interacts with concerns about inverter-based generators somehow, but I'm like, what is the relationship there?
Yeah, I mean, the relationship is that in a similar fashion to how the computational loads don't provide this kind of synchronous and inertia-based interaction with the grid, the inverter-based resources, they aren't the same as your traditional synchronous generators, your gas, your coal, your nuclear, that have physical inertia, which is, the rotating mass of the turbine resisting frequency changes. And so if a large load suddenly disconnects or a generator trips, inertia buys the system a few seconds to respond. In the same way that computational loads don't have that, these inverter-based resources, your solar, wind, and batteries, they don't have that by default. And so it is actually somewhat analogous in some ways to the challenge here. And I think there are threads that you can pull on that make it relevant to the level 3 alert for the inverter-based resources that NERC put out. But there are, we've flagged some of them already, the scale and the speed at which these things can drop off.
So this gets to, we did a pod, I don't remember, last year at some point, about grid forming inverters, about the ways that inverters can be programmed to provide inertia. We call it synthetic inertia. And it seems to me like the scale of this is like you're either going to have to build a lot more spinning masses. It seems like a more practical and viable solution to me, especially given there are more and more and more inverter-based generators coming online, to just like make sure all those inverters are programmed to respond to this with synthetic inertia. In other words, it seems like although they are a worry now because they don't provide as much inertia and all of a sudden we need tons of inertia, in the long term, it seems like inverter-based inertia is going to be a better solution. Does that ring true to you guys?
I do think that's basically true. And there's some interesting lessons maybe from history here. About a decade ago in Germany, there was an interesting problem called the 50.2 hertz problem. 50 hertz being the European grid.
Right. Ours is 60, theirs is 50.
Yeah, exactly. And on the German grid, a lot of rooftop residential solar power systems were being installed, and they had inverters to convert that DC power to AC. And those inverters had initially been programmed with a very hard cutoff when they detected the frequency of the grid that they were trying to send power to. When they detected that rising above 50.2000 hertz, they tripped offline. They stopped sending power to the grid. And nobody cared about this in the first couple of years because there weren't very many of them and it didn't really matter. But the problem began to snowball, and grid managers realized that since every single one of them was programmed exactly the same way to trip off at exactly the same, you unintentionally created the synchronized trip-off effect, which really could have cascaded. And the point for our conversation here is there was a solution, and that was to reprogram those inverters to sort of have essentially a scramble, a little bit of randomization on the exact number, so they weren't all perfectly synchronized. But that was a software push, more or less. And when you're looking at trying to deploy big changes to the grid, I think I would probably take a software update over some sort of hardware install any day of the week.
Yeah, it is sort of like a mirror image problem.
Yes.
And it's kind of is being solved on the inverter side, is being solved on the supply side.
Yeah.
And basically just, we need to have a similar solution on the load side, more or less.
It's worth mentioning that there are some grid regions that have implemented these voltage ride-through requirements for large loads. Not very many of them, but there are some sort of early adopters here. Southwest Power Pool, you're seeing German FinGrid. The problem is that those are scattered. There are not very many of them, and they're not the same. So they've set up different ride-through and different reconnect requirements. They're not following a consolidated standard across the industry.
This brings us quite smoothly into what NERC wants people to do. There are 7 core recommendations. Maybe we could just walk through. I mean, and they're really like everybody involved gets some of these recommendations. Like nobody escapes NERC's eye. These are transmission planners and utilities, regulators.
Yeah, there's about a dozen acronyms at the top.
Yes, this was a real acronym soup. Everybody involved in this world is being asked basically to do something. So maybe just walk through some of those recommendations, like who's being asked to do what here.
Yeah, so as you said, the 7 essential actions, they're kind of bucketed into, I'd say, like communication and modeling and then actual operational implementation. On the communication piece, there's stuff up front that, the first essential action is essentially that planners need to collect the right data from data centers. So they need to be able to define exactly what technical information they need from computational loads and require transmission owners to collect it as a condition of interconnection. So that's right out the gate something that, in some jurisdictions this is being done, but it is a prerequisite to all the rest of them, I would say.
And presumably you're going to want to sort of standardize what that information is. Like you're going to want for computational load to have a sort of standardized set of data that they provide, ISOs and the like.
Yeah, so I mean, this is an interesting one, and I want to get Colin's take on this. Is because as we were just kind of discussing it a bit earlier, is there's a kind of baseline here. Like for example, the types of grid stability studies that they expect to be done, and they provide a recommendation of the type of modeling, but the language, it isn't fully prescriptive. It's not saying like here is exactly the process that needs to be done, and some of the language leaves it up to interpretation to the extent that we may end up with more data points to what Colin was talking about around the ride-through approaches, but they won't necessarily be
right
homogeneous.
And when you're talking about who's developing these standards, is this the wholesale grid operators, the ISOs and the TSOs? That's who we're talking about?
Yes, they would be in charge of developing those approaches. They're regulated under FERC, other than ERCOT. Well, actually, no, ERCOT would be for this particular thing because it's a NERC reliability standard.
And so that's one of them. Better information from computational loads.
Yeah, the second one is running grid stability studies. So basically simulating these exact instances and being like, how do we have the mechanisms in place to deal with it, and helping identify where the grid is vulnerable. So planners have to model what happens to the grid if a large amount of computational load suddenly disconnects. So a trial run for what we are actively seeing it, but trial run so that they can hopefully mitigate it.
And that's also the ISOs and TSOs being asked to do that.
Yeah, that would be right. Yeah.
Another one is commissioning. What's that all about?
No, I think this is a very interesting one. So commissioning is a concept you get with a lot of construction projects. When you're finished with a commercial building, you need to run through a commissioning process before you actually deliver it. And that's not necessarily in place or standardized for data centers connecting to the grid. This commissioning recommendation is saying that essentially you need to be evaluating the as-built data center, the electrical characteristics, and how it will actually respond to grid disturbances in a not purely a modeled sense,
right.
Also actually as built. And you need to iterate or refine your model based on what's actually in the facility. I will say one fascinating thing I find in this is there's a push to do this, where possible, full facility load and no load test should be done with all the compute equipment in place. Interestingly, we often see data centers built in phases.
Mm-hmm.
Yeah, right. Yeah, that's what I was going to ask. Like, do they have all that together in one place before they connect?
No. And I think this opens a really interesting set of questions. So does that create this issue where grid operators are going to have to kind of continuously commission or revisit commissioning as new computational load is installed? And you could argue that's a very good thing to do from a grid stability point of view, but it's a complete pain in the you-know-what from the data center operator point of view.
And that's a distinction that I would make between what the NERC alert recommends and so in ERCOT, there's a proposal in place for grid ride-through, and it's only for new interconnections. Whereas this is saying at the very top, there's a line that identifies it that says this is for both existing or new and existing computational loads. And I think one of the essential tasks is actually redefining what counts as a change. And it's basically broadening that definition so that more things count as a change, and so it would be required to be reviewed through this process.
Yeah, it seems like you're going to get into fuzzy territory here. Like if you're just sort of adding, you can sort of imagine a data center sort of adding just kind of one rack at a time. You can imagine these incremental changes, like how big of an incremental change triggers a new commissioning requirement. That just seems tricky. It's very tricky to me. So those are the informational, the communication, the modeling ones. The next one on my list is protection. I'll just throw that out. What does that mean?
So I think that's evaluating and addressing the ride-through gaps. So, planners have to identify where data centers would trip off during a routine fault and work on fixes to prevent unnecessary disconnection. So more kind of operationalizing the grid stability studies that is done in one of the previous stages.
And then fault recording. What's that?
This gets to the point of how complex some of these UPS, these uninterruptible power supplies, potentially can be. They're highly active devices. They can not only, as I mentioned, sense frequency and voltage, but they'll include sort of smarts like incident counters. So they may actually not trip off the first time they see a voltage fluctuation, but they may count up, oops, I saw 3, I saw 4 within 2 seconds. Now I'm out. And that kind of behavior is very complex to model if you aren't aware of the very specific logic in the UPS. And to really sort of trace the root cause of events, you would really like to have very high time resolution data on what was actually happening during that dynamic fault event. You'd really like to have granular time-based information on that. And that's what the spirit of this recommendation is install equipment that can really record that data to be used in root cause analysis after the fact.
All of these so far sound like basically like informational, like better modeling, better communication. What are they recommending physically for computational loads to do?
This is a bit of what Doug and I were talking about earlier. If you look at the language here, you might think, coming to this, geez, NERC should have said voltage ride-through sounds really important for large loads. We're going to be a little bit more aggressive about saying that voltage ride-through is either mandatory or strongly encouraged. Large loads shouldn't be allowed to interconnect to the grid until they demonstrate they can perform voltage ride-through in certain conditions. That's not where the language has landed. It's a lot more gentle. Coordination with computational load customers where possible to maximize the ability to ride through. So there's a lot of reasons for that. Doug mentioned earlier the concerns from the data center industry, large load industry about how feasible this is in the short term. There is also the lack of a centrally recognized standard that everyone can consolidate around. You might look to IEEE or some other credible organization to kind of get that in place before you try to lock in or mandate something. So I think we're seeing a little bit of trying to be sensitive to that issue, push a little bit, nudge now, but not lock in a hard mandate without the remainder of that ecosystem in place.
And it's probably also a function of where in the process this alert falls, right? Grid entities of many shapes and sizes have until August to respond to this. Following that, there will be new reliability standards drafted. And unfortunately, with these processes, it will take a couple of years for this to be enforced. Like you wouldn't expect it to be enforced until I put myself on the spot, but 2027, 2028 is probably like a realistic time frame.
These are gentle recommendations, but presumably this is part of a process that is evolving in the direction eventually of requirements, real requirements. Mm-hmm. So this brings me to sort of FERC. What is FERC's involvement? in all this? Is it the case that like once some of this gets worked out a little bit, FERC is going to be the entity to implement these requirements?
Yeah, I mean, typically that's, I guess, the NERC to FERC pipeline.
Right.
NERC develops reliability standards through these processes and then has to submit them to FERC for approval. And then once FERC approves a NERC standard, it becomes mandatory, and there might be financial penalties for not subscribing, et cetera, et cetera. So this current guideline, right, it's a voluntary guideline, is a signal for what the mandatory standard will look like before it actually, arrives in force.
And I think relatedly, what is the Large Load Working Group? Is that FERC related, or is that pre-FERC in the NERC to FERC pipeline?
Yeah, it's a NERC initiative. I can't remember exactly when they started, but I think they were like the Large Loads Task Force, and now they're Large Loads Working Group. And they've effectively been publishing white papers and guidelines. Like they were in charge of the associated reliability guidelines that came with this, that talks not only about these super short-term events, but also how you bake in these computational loads into long-term resource planning. They had lots of things to say about load forecasting, and NERC has been generally like quite. They've had a lot to say about how the approaches to load forecasting are not sufficient going forward because of the event we find ourselves in.
Yeah, I want to return to that in a minute because that's a super interesting question. But one of the questions this raised, and I guess this would be a good time to ask it, which is a lot of this sounds like the hyperscalers who have just been out basically cowboying up and throwing these giant loads on the grid and like throwing gas generators all around them. And just there's been a real Wild West vibe to all this going on. And here comes the dreaded nanny state coming to tell these cowboys, like, get your shit in order here. So I sort of wonder, what is the hyperscalers' attitude toward all this? Because I don't see how this is going to avoid ending up in a situation where basically you, as a data center developer, as a data center operator, are going to have a lot more work on your plate. Basically, you're going to have to do a lot more data gathering, data reporting, et cetera, et cetera. I wonder, like, what's their kind of disposition toward all this?
Yeah, I would definitely use the case in the States that is furthest along on this file is that ERCOT proposal, that ride-through proposal. And it's in its second or third iteration now. The first proposal, the Data Center Coalition, right? So that's the kind of groups that you're referring to. They filed these formal objections to the original proposal, and it largely centered on the hardware damage argument.
Yes, well, this is my question. Like presumably there's a reason that they trip off so easily, is that they're protecting extremely expensive and valuable equipment. Can you ride through and ensure that equipment is not damaged? Like, presumably they're a little sensitive about this.
Yeah, certainly. And, whether or not the equipment is, the equipment is expensive, but it's what the equipment is doing.
Yes, right.
That is, right? Like that is part of the arms race we live in, which is ensuring that you're serving the AI loads that are coming through your system, be it inference or training. And so it's a similar reason why there's been challenges in getting, typical like demand side response mechanisms, which are price based. You're dealing with entities that set a very high value on the power because it's delivering these services that are obviously the apple of the market eye at the moment.
I think it's entirely feasible to design these systems to ride through better. It's not impossible to design UPS systems to do more ride through, except a wider tolerance band. They've just always been governed with a different design principle in mind. They've been built according to something called the ITIC curve, which specifies a little bit of a conservative view about when to trip off. But from an electrical engineering point of view, it's certainly not impossible to build more protection and to allow longer ride through. It's more of a question from the hyperscaler point of view about the availability and the validation of those devices. Thanks a lot, ERCOT or whoever, you told me I have to go do this. Who can I buy them from? Have you qualified them? That's a supply chain headache I don't want. So I think you need to look more to that than any sort of fundamental electrical engineering limitations.
Well, this again tees up my next question really well, which is what physical or electrical engineering changes can hyperscalers make to be better grid citizens? Here on Volts, one of our slogans is it's all really just batteries in the end. So I'm wondering, is this also in the end just more batteries? So what do we want computational loads to do in electrical engineering terms to be better grid citizens? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition, and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. Here on Volts, one of our slogans is it's all really just batteries in the end. So I'm wondering, is this also in the end just more batteries? So what do we want computational loads to do in electrical engineering terms to be better grid citizens?
It is in many ways all batteries in the end, although there's we can talk rectifiers and inverters as well. Yeah, I think there are, first of all, software updates. So for example, the idea of these event counters I mentioned earlier in the UPS logic. Gosh, I saw 3 or 4 events within the same 4 seconds. I'm taking that as a sign something large is wrong. I'm tripping off. You can just change that in software. You can just not have an event counter or not include that as one of your trip off. That's a software update. And indeed, that would likely, that would be one contribution to being a better grid citizen. What you're otherwise talking about is putting more stress on the battery component of the UPS, banging on that a little bit harder, or at least accepting a little bit higher risk that that's going to have to absorb voltages or frequencies outside of a current comfort range. That can involve equipment updates, that may involve somewhat modified designs in the electrical engineering. Those are two sides of the sort of software update and hardware update that would apply.
Is anyone talking about trying to make the compute itself more flexible?
Well, at a macro level, absolutely. Lots of interesting ideas about, and we're seeing them implemented, about scheduling big compute jobs. And there's a lot you can do on that. It's terrific to see some work on that. That involves planned flexibility, right? So not, responding to unexpected events.
Well, just like you were saying, they were asking inverters to randomize a little bit, not do all the same thing at the same time. I mean, you could see as kind of a similar thing on this side, right? Like randomize your compute loads a little bit so that they're all not doing the same thing at the same time.
Yeah, no, that's an interesting idea. I think that randomization would apply more in these UPS systems that are facing the grid. So some percentage of them would trip off at low, minor voltage, or there would be sort of a scatter of their thresholds to trip off. I mean, another challenge that we didn't even mention this earlier, there's equipment damage, but compute loads that are in the middle of some complicated computation and have a lot of sensitive data in active memory, if power goes down, that data is all gone. It wasn't written to drive. So you get data corruption. Even if the physical system isn't damaged, you get data corruption. You obviously get loss of service if these are cloud servers. But there's a range of concerns that have motivated the the data center designed to be very conservative about.
Yeah. It's like playing a video game and you have to go back to the previous checkpoint.
Yeah.
And you realize that it's very far.
I lost all my progress.
That's right.
All right. I don't know. I'm not sure if this is the time to raise this or if this is even relevant here, but there's a lot of talk about the distinction between co-location and behind the meter power responses. What is that distinction and how does that play into all this?
So the behind the meter concept is, of course, having generation on site, but on site in such a way that it's electrically connected directly to the load. It's not going out to the grid and then back. And I think in the extreme case of that, what we might call a fully islanded system, where the data center has literally zero connection to the grid, then this problem essentially goes away because the data center is no longer connected.
Nobody's really doing that.
Ain't nobody going to really do that. That's exactly right. So that's an extreme case that's silly to think too much about. I think what we're looking at more are these hybrid arrangements where you've got on-site behind-the-meter generation, but you also have a grid tie. And there's reasons to believe this could actually make it a little bit more problematic because that's an even more active system. In cases where that behind the meter facility is providing part of the load and the grid tie is providing part of the load, that mitigates the problem because the data center is using less grid power than it would in another context. But it makes it a more complex problem because you've got more pieces of the puzzle there to balance out.
Yeah, and all these regulations that apply to generators to try to make them good grid citizens, are they applying to these generators behind the meter?
I would say that's an aspect of the NERC alert that we haven't fully touched on, is that it includes they want to see the full apparatus. They want to understand in your campus, what is everything going on there, including any co-located generation. And so I think that has dual purpose, right? One is, are you therefore, if you have sufficient backup generation, are you therefore more likely to trip off and have more sensitive tolerance to that? And then also to Colin's point of what is then the interaction between the generator that is behind the meter and the load that we are servicing as the grid operator.
But as I understand it, they're insistent on the difference between behind the meter and co-located, which is one of the things I'm groping. What does co-location mean in this context?
I mean, I would view it as the data center is physically sited at a power plant or vice versa, and it takes power directly without it flowing through the transmission system.
Right, but not behind the meter, but not behind the data center's meter, just literally physically located next to a power plant, which is also, but the power plant is hooked up to the larger transmission system.
You're right.
And so is the data center.
Yes. So that would be the case I gave is the full behind the meter case, the co-location case, which is, relevant for, I think the FERC directive to PJM to develop these co-location tariffs. And obviously I'm sure you've done another pod on this, on the PJM tariff discussion, but that is more about, okay, how do we then interact the co-located resource, the load, and the service firm or otherwise that I will receive from the grid. So I say that's kind of how I would view them slightly separately.
And at some point in one of these PDFs,
sorry to give you a big syllabus of reading there.
I can't keep them all distinct in my head, but somewhere I saw demand response brought up and referred to in this context as a ghost battery, which I thought was fun. But what?
I think that was my term, so I'll take credit for that.
Oh, good, nice work. I love a good new term. What is the operational relevance here? How is demand response? Volts listeners are very familiar with demand response, which is just, demand ramping up and down in response to grid conditions, as opposed to just generators ramping up and down. How does that interact with the data center mess specifically?
Yeah, it's definitely under the umbrella. This whole conversation is related to data center flexibility. It's, you are either flexibly interrupting the power supply and going behind the meter, or you're flexibly responding to grid constraints, prices, what have you. The distinction I would make is that most of the conversation around demand response is occurring in these planned, as Colin put it, right? These planned responses, whereas this is flexibility of a different type. And it's arguably by dropping off the grid, which is what you want in some of the planned cases, you're creating problems. So they're under the same umbrella. And in fact, I think there's various initiatives going on, like the EPRI DC Flex initiative. Like they look at both. They're considering the array of this challenge and not excluding one for the other, but they are certainly different.
Is there such a thing today as demand response of any scale that is capable of responding at the level of milliseconds and seconds? Like, is that even a thing that computational loads could procure if they wanted to?
I mean, without going back over this, I would argue that that is what the uninterruptible power supplies are doing. Like that is their demand response in a way of like responding to an issue in these sub-second or second intervals.
Well, I guess what I had in mind is like, you could say as a computational load, like if we drop off, if we have this other demand response out there, demand response is not just demand decreasing. You could potentially say, hey, we'll ramp up demand elsewhere to compensate for this. I just wonder if that is even like a possibility.
I would frame that as the current sort of frequency stability ancillary services market, where some very fast responding asset like a battery or like a flywheel is essentially on a very short time scale ready to ramp up or down to respond, sort of seconds to respond to small mismatches.
Yeah, I guess one way of putting this is like ancillary services are, in my understanding, are mostly out there doing relatively small scale work. It just seems like if you're putting gigs, if you're involving gigs, all of a sudden ancillary services, you need a lot more of them.
Yeah, that's right. I think the ancillary services market is growing, right? It's growing in volume and price. The type of resources on the grid might be saturating that. So like batteries, for example.
Yes, I mean, one of the sort of critiques about the economics of batteries, people are always saying, oh, batteries are value stacking. They have multiple values. One of the things they can do is play in these ancillary markets. And then the response to that has always been, well, you put a few batteries on the grid and you basically saturate the ancillary services market. And then it's not a value for any batteries beyond that. But if all of a sudden ancillary services markets are like booming in volume, all of a sudden, again, lots more batteries. Well, you're back to lots more batteries as your answer.
I think maybe I'll put my more engineering than economist hat on, but I think trying to build a gigawatt scale ancillary services market to protect against this possible load trip issue is probably the wrong direction, unscalable. I think this is what motivates the look at the ride-through requirements and the engineering solutions at the data center, rather than trying to stand up this separate.
Right. So that was sort of my question. Like realistically, you're not going to get gigawatt scale ancillary services that can respond in seconds,
and wildly uneconomic to pay them to sit around, in case. So yeah.
Right. Sit around for completely unpredictable.
Exactly. Yeah. So
in sporadic events. Yeah. So it's mostly going to be solved at the computational load level.
I did want to touch on one sort of mirror image aspect of this, which Doug mentioned earlier, but we should expand on a bit: the reconnection problem. So here you've got a data center that's tripped offline because of a problem, and maybe it was justified, maybe not. It's going to come back. Well, and there's a big issue. So is it coming online? As soon as the internal logic in that UPS says I'm good, it just 100% back online. Well, if that happens in a synchronized way across a gigawatt, that's just as big of a problem as tripping off.
Right. Then you have grid operators telling a gigawatt's worth of generators, come online quickly. And then like seconds to minutes later saying, okay, go back online, go back offline quickly.
You gotta smooth that out somehow. It's just crazy. Yeah. So the problem is there aren't broadly accepted standards of exactly what that looks like. And you do want to get them back online, but you've got to think carefully about how to do that in a smooth way that doesn't put you right back in the hole. And so that we see in this discussion as well, the ride through, but then the reconnection piece is sort of less intuitive, but just as important, or else you're recreating. It's the mirror image of the trip off problem.
Right. These are not even ramps, really. These are like cliffs.
Well, they could be ramps. I mean, that's sort of part of the thinking is that maybe there's a maximum ramp rate that the UPS is allowed to do, and then that's a potential solution.
And that's a problem that is actively in these discussions, right? Like I think we focused the conversation on ride through and that full tripping. But what I mentioned earlier around the training loads and how they spike and dip, And it's exactly that, those ramp rates. And there are guidelines for how fast load should ramp up and down. And in some cases, they're outside of those regulations.
Right. Generators are supposed to ramp up. Like, as we say, our generators are already under a lot of regulations, and they are not allowed to do these giant cliffs.
Yep.
So speaking of like what people are doing about this, you mentioned that ERCOT has some regs in the works. Presumably state legislators and regulators, everybody in the world is freaking out about data centers, freaking out about computational load. Like what are states doing about all this? Like there's all these bills I know about data centers, like basically in every state legislature at this point. Like, is this part of what's in those bills? What are state legislators and regulators doing right now?
Well, we've taken a look at this to some extent, and largely these reliability issues are not in the purview of state legislators. They're not necessarily front of mind. Maybe in the last week or two, given the NERC alert, that's begun to change. But the focus of the legislation has really been around environmental impacts of data centers, power price, sort of raw power, consumer power price impacts. And then on the flip side of the coin, you see plenty of efforts at the state legislative level through tax credits or other things to attract data centers to the state. But these reliability issues are really out of sight for many policymakers. And maybe we're going to see some motion on that. At the same time, NERC is doing its job. These are highly technical issues, and they probably should be largely addressed at the existing level of NERC.
I almost wonder, like, from the state perspective, like, it seems like one of the things, if you had sort of like godlike powers over all this, like one of the things you would do to increase safety is not cluster these loads geographically. It seems so that they're all on the same grid. It seems like you might want to geographically disperse them. I have no idea sort of like what regulatory lever you would pull to do that, but is that even on the table?
Well, a couple thoughts on that. There's an engineering reason for that. So voltage disturbances tend to be more limited as the scale of the grid, whereas frequency disturbances affect the entire balancing area. So yeah, if you can get outside of that sort of radius. On the other hand, many jurisdictions, want to attract data centers. Data Center Alley in Virginia is the grandfather of them all.
Yeah.
I mean, that's the exact opposite. So I think you do have a little bit of a collision of the economic arguments around wanting a tax base, wanting whatever it is to cluster, and then these grid engineering arguments of no, please keep these a little farther apart for these stability issues. I think those are unfortunately kind of in tension.
Interesting. And just maybe listeners have this question on their mind. Isn't this a podcast about decarbonization? So this has been mostly just about electrical engineering and about data centers and their effects on the grid. But
on the contrary, David, it's called volts, and we are talking about voltage rises.
We are very much talking about volts here. But is there a decarb angle to all this? Like lots of data centers seem to be lunging for gas. And like in ERCOT, the number of gas entries into the interconnection queue is up 150%. And like some renewables are withdrawing from the interconnection queue. And it seems like at least the hyperscalers are looking at gas as a reliability solution that they need. That is distressing. I guess I just throw it out as a general matter, like, how can we respond to these issues and regulate in such a way as to include decarbonization in the conversation, as to steer things toward renewables and batteries rather than gas plants?
Totally agreed that this needs some more thinking. And I'd argue the economics are a piece of this. I think we are going to see that the renewables and battery side in the long term is winning out on costs, and hopefully that'll drive some thinking.
I hope that's true because I say it like 50 times a pod. But that doesn't seem like what they're doing right now. You know what I mean?
A lot in the queue. And of course, we'll see what's completed, what supply chains for turbine equipment enable. We've taken a look at the projections for new gas production. 10, 11 BCF a day is what you're seeing from queue. That's a lot. There's a lot of upstream methane leaks to think about there. On the other hand, delivering that requires gas transmission pipeline, distribution infrastructure that doesn't necessarily exist. So I think it's hard to project a real completion rate. I do wonder how much there's a world of kind of zombie gas projects or partially completed ones where the economics don't make sense 1 or 2 years in, 3 years in.
But can you explain what is going through the hyperscalers' minds that they are going for gas?
Well,
what are they thinking?
So, you mentioned reliability from the perspective of the data center. I'm not worried about the rest of the grid. I'm worried about enough power for me. The solution of having my own on-site generation kind of seems good at first, and I can see the appeal in the near term. I kind of want my...
And to some extent, it seems to like free you from some of this nanny state regulation of the grid, right?
I think that's a mirage, though. So you do still have to get the gas on site, and that involves working with pipeline permitting and construction potentially. So I think if you want to use the nanny state metaphor, I don't think you're necessarily getting away from that fully.
At the end of the day, firm power is hard to procure, and I think that's largely the reason for going so all in on gas. I'd say my take on the decarbonization angle is that, kind of back to what Colin said when we were talking about, and David, you prefaced this, you were like, is the solution batteries? It always seems to be. Well, we're making leaps and bounds in long duration energy storage technologies. They are really having a big moment.
Yes. Upcoming pod on that, by the way, the role of long duration energy storage in this data center mess.
Perfect. I'm sure you'll discuss on that. They can do a job in firming up renewables and providing that firm power, and potentially play a dual role. Like the uninterruptible power supplies, it is switching to batteries. Like that is often the means of switching. And so I think there are links to decarbonization solutions that are burgeoning at the moment that could play a role here beyond what we're seeing today.
Yeah, I always wonder, people talk, these hyperscaler guys talk about firmness as though it's some magical quality. I just don't know what firmness you're getting from gas that you don't get from storage. It's the electrons are the same. If you can call on it and it provides you the electrons, then it's firm. It's hard not to see an element of, let's say, masculine energy involved in preferring gas or nuclear for your firmness over batteries. But operationally, they're both firm, right?
I'm sure the folks at Form Energy would fully agree with you. And the challenge up to now has been the duration, right? And the cycling, and we're potentially finding solutions to that.
Well, also, I'll just add, as we think about these questions of how inverter-based resources can be reliable on the grid and how these similarly power electronics-based loads can be reliable on the grid, working through those engineering issues and showing that a inverter-based renewable resource and large loads behind power electronics can work reliably as long as standards are aligned and we solve some of those. That's an important piece of getting towards that decarbonized grid, of giving engineering confidence that, yeah, we can do this. We just got to work through the problems.
I always take the long view that this challenge it's acute and it's here today, but it is something that long-term decarbonization requires us to figure out, because much of the solution to decarbonization is to electrify. And yes, we are receiving the load, and it is at a scale, at a speed that we did not expect, but they are challenges that we're going to have to resolve, and that's how I would take it as a reason to pursue, and why you can link this back to still being a somewhat related decarbonization episode.
So let's move into, I think, sort of the final cluster of questions, which have to do with, so if you are requiring all this of hyperscalers, a bunch of new reporting, maybe some new electrical engineering requirements, maybe more batteries on site, there's no way around the fact that however this settles out, it's going to be there's going to be more requirements and obligations put on the back of hyperscalers. And then you would think the sort of inevitable result of that is going to be that it's going to be a little bit slower. If the ISOs and the utilities all have these new reporting requirements, they're all communicating more, they're all doing more modeling and better modeling, et cetera, et cetera, et cetera, it seems inevitable that that's going to slow stuff down. So then you might think, well, these projections people have of massive data center demand coming online, well, maybe these projections need to be scaled back a little bit. And then you get in this weird recursive thing because like modeling future demand is part of this now, but like the requirement to model it is in some sense affecting how fast it's going to happen. So like, is it fair to say that all of these requirements, if put into place, are going to slow the rush to data centers, and thus that some of these wilder projections are probably not going to come to pass?
Who would be an energy system modeler, hey? Especially a long-term forecaster. That sounds like a terrible occupation.
This is your job, Doug. I want a firm and clear answer on this.
So, yeah, I think it's a very difficult thing to foresee. And what I liked about the NERC alert is that they paired it with these reliability guidelines that really had a bit of a playbook for how they think we should be thinking about load forecasting approaches when it comes to data center load. You know, we've talked about this, Colin and I, internally, that there's a few ways you can forecast this. So you can look at hyperscaler CapEx announcements and SEC filings. You can look at the GPU and chip shipment data. And then you can also look at the interconnection queue, although typically you have to provide a pretty significant haircut to that. I'm inclined to agree with you that it creates more obligations and challenges to getting interconnection, such that it makes that job even more difficult to do.
David, I'll give maybe a bit contrarian perspective, which is I actually think the incremental effort here is pretty minuscule, especially compared to the other challenges that rapid data center build out already faces. So getting sufficient switchgear and transformers.
Yeah, there's all these supply chain challenges
Yeah.
that people are, and especially if you want to run your thing on gas too.
That's
a
right.
huge supply chain constriction there.
So, I mean, I would argue that the headaches that these requirements create are pretty far down the list of stuff that would slow a project down. The way it could turn into a headache is if a mandate were put in place prior to a clear standard and compliant equipment being broadly available on the market. So if the regulators get it wrong and get ahead of where feasible solutions are available, then yes, it can turn into a headache. But in and of itself, I think if compliant voltage ride-through compliant UPSs are available, a data center project developer can probably get by specifying what they are, providing a little bit more data and to the grid operator. And I think that's actually a relatively minor lift compared to all the other headaches high up on the list of that project.
But yeah, like Carbon Direct, your firm, one of the white papers you sent me says pretty flat out that like a majority of the data centers in the queue are probably not going to get built. So like, why is that?
Oh, well, that's a whole podcast of itself. I mean, I think there's...
it's the other hassles outside of this?
I think those are heavily other hassles are driving that. I mean, grid reliability is an important thing to think about, and we see it growing, and that's why it's great that NERC's applying here. But the compliance requirements, I think, compared to the other headaches of securing sufficient bulk power at all sites, securing, like I said, switchgear and transformer equipment, other equipment shortages, those are slowing down projects today in ways that are far more substantial. So I would argue that the ask being made of the hyperscalers, while I agree there's a pain in the ass factor, is not that severe here. There's a lot of benefit to grid stability that can be done with a pretty light lift.
But it is the position of Carbon Direct that the wilder projections of data center load are overheated.
It's a position. I mean, I think our analysis shows that there's a lot of load being added. But yes, if you took the outside numbers, no, those are pretty far off base. We're going to see a lot of load. And also, if it's a 40% completion rate, that's still an enormous amount of load compared to historical. So getting too wrapped around the axle on this, I think, is not merited. There's a huge planning challenge to be met here. But yeah, the outside numbers, our analysis shows, don't take those to the bank.
Okay, really final question, which is, we've done pods a lot on like EV charging, and sort of the kind of TLDR on large scale EV charging is if you do it in an uncontrolled Wild West manner, it could screw up the grid badly. But if you do it in a planned and rational manner, not only could it not be a detriment to the grid, it could prove an active help to the grid. Like you can use, it can be a tool, an active tool for grid stability and for grid reliability. And I just kind of am wondering, is the same true of computational load? Is it the case that if we get this right and the right requirements are in place, that computational load could be an active help for grid stability and reliability, or is that too optimistic?
I'll start and let Doug wrap up. I agree very strongly with that. Computational loads sitting behind power electronics, if done right, can absolutely be a positive contribution to grid stability. And that involves shifting some of the design basis so that it's not purely about extremely conservative protection of sensitive compute equipment. It's about also taking into account riding through faults and potentially some active grid stability support through frequency reg or other similar kinds of things.
I mean, if you could make a gigawatt scale data center into a demand response tool, that's a giant demand response tool.
Absolutely.
Like the stack there, right? It's almost of a VPP. You've got on-site generator, you've got battery backup systems, you've got, in some cases, controllable flexible load, and then you've also got fast responding power electronics. So I know you've done pods on VPPs, but that's a decent recipe for being a grid asset. So I would concur with Colin on that.
Well, that seems like a good optimistic note to end on. My audience does not always respond well to optimistic takes on data centers. There's a lot of, I mean, whatever else you can say about hyperscalers, they have not done very good PR for themselves. They've not told their story very well. But like, if you can get multiple gigawatts of new load to be responsive and responsible, this could have a happy ending.
I think so. I mean, David, I'll just say, I think that's the details are so nerdy here, and trying to even grasp why this matters. I mean, Doug and I were talking about this fun analogy, the bicycle analogy, about when you were a kid, you might have ridden one of these bikes with no gears and pedal brakes, and when you got going on those bikes, blazing downhill, and those pedals are whipping around there. If you take your feet off the pedals, the bike speeds up. The frequency speeds up because it's not having to sort of carry the load. And then if you want to put your feet back on, you damn well better be sure you're synchronized with those pedals, or it's gonna really slam into you and hurt you. That's what's going on here on the frequency side about connecting and disconnecting from the grid. And this is often not very sort of physically intuitive to people about why any of this matters. Just, it's just about total megawatts. And conveying that a little bit might help open up that.
So you need gears.
Yeah, sure. Yeah.
And more sensitive brakes.
Something like that, yeah.
We have family injuries to attest to the just the problem you're talking about.
That's right.
All right, guys, this is so fascinating. Thank you so much for coming on and talking through all this with us.
Thanks so much, David.
Really appreciate it.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.